chapter 21, and here we will be able to study the electric force and how we are going to calculate the electric force, and that is going to be using Coulomb's law. We will be able to find the electric force, calculate the electric force for a point charge, and also we will be able to calculate for a distribution of charges later. We will talk about the electric field calculation. Now, Coulomb studied this interaction in 1784, and he did use something similar to what you can see in front of me, which is called a torsion balance, similar to the one that was used by Cavendish to study the gravitational attraction. But here, of course, he did use point charges, and Coulomb found that the magnitude of the electric force is inversely proportional to the square of the distance between the charges. And this is, I will say, something that all the forces they're gonna satisfy. Then that force, which is, I will call it the force electrical, has to do with the multiplication or the product of Q1 and Q2. And it is like, okay, there is an inverse proportionality with R squared. Now, something that we need to know that we can combine these two together, and then we can say that if E equals a constant that multiplied by Q1 over Q2 divided by R squared, and here I will say what are the charges, positives together, negatives together, one negative, one positive. I will say this is Q1, this is Q2, and these are really the charges measured using coulombs, the unit of charge. And that is really, as I said, the Coulomb and we characterize it by uppercase C. Also, that R, it is the distance between the two charges. Now, that K, the constant, okay, was calculated to be also using another constant, and that is, we call it epsilon 0, and that epsilon, it has to do with the medium, and therefore we are going to say mostly now the medium is going to be air. Now, epsilon 0 here, we call it the electric constant, and that value, of course, you don't have to memorize. You should be receiving that in your exam. 10 to minus 12 Coulomb squared, Newton times meter square, and K, when we're gonna have that calculated, K electric, sometimes we call it, it is 8.988 10 to the 9. Now, one of the things that I want you to know, that the electrostatic force or the electromagnetic force is the second in strength among all the forces, and this is because of that constant. Now, if you compare this with the universal gravitational constant, which is 6.67 10 to minus 11, which is actually the one that is making the gravitational force the weakest, and this constant K electric is the one that is making the force of the electrostatic force as, the second strongest. One of the things also I want you to know that most of the time we are going to have more than charge involved, and therefore I need to find what is really the net force. Therefore I want you to maybe review how you are going to calculate what is the net force on an object. For example, like here I'm just showing you, for example, like you might have a square and you have one charge here, positive, one negative, one positive, one negative, whatever, like, and then I'm asking you what is really the forces or the force on this charge. And here I will say, you are going to put yourself in the place of this charge, and you are going to say, okay, I'm gonna feel attraction from this one, then F1. Okay, then I'm attracted to 1. Okay, I am also repelled by the second. Then there is this line connecting them. Then this is F2, and of course based on the magnitudes, these, like I will say, vectors, they're gonna be different. And I will also be attracted to this. Okay, then here I have the three forces acting, and most of the time there you should have kind of understanding of the basic geometry, how to determine the angles. For example, here, like this is 45, and maybe also this one is going to be 45. And then you can work on the components, which means your Fx, the net force, is going to be sigma Fx's on all the charges. And then it's gonna be F1 cosine theta 1 plus F2 cosine theta 2 plus F3 cosine theta 3. Here I'm using the angle with respect to the positive axis, counterclockwise direction. And Fy is gonna be sigma Fyi, which is gonna be F1 sine theta 1 plus F2 sine theta 2 plus F3 sine theta 3. And then finally I can calculate the net force as the square root of Fx squared plus Fy squared, and the angle as tan inverse of Fy over Fx. Now this is just briefly, like showing you, but this is a needed skill for calculating the forces, the net forces, and also the net electric fields. Here, just also one thing that we need to know, very similar to what we did with gravitational force, that the magnitude of the electric force between the 2-point charges is going to be the same on both, which means it's a mutual force. F1 on 2 equals F2 on 1 as magnitudes, and the minus here just to show you that they are really opposite in direction. Then this is really in Newton's third law case, where we're gonna have forces acting between these two forces, and they're gonna be equal in magnitude, opposite in direction. Now also here I'm showing you what is really Coulomb's law problem solving strategy, where you need of course to sketch the location of the charged particles and label each particle with its charge. If they are not lying on the same line, you should set an XY axis thing. okay? And the problem will ask to find the electric force on one or more particles, and then I need to identify what are these unknowns. Now, I will say you need to sketch a free body diagram showing the electric force vectors acting on each particle of interest and the force exerted by particle 1 on particle 2 points from particle 2 towards particle 1, like as I did show you before. You will use the principle of superposition, which I was talking to you, sections 1.7 through 1.9, which is really the methods that they are going to be about adding vectors, but mostly I will say we will use the adding pi components is going to be the easiest when it is two-dimensional problem. Also here, we are going to use the K electric. I use it simply as 9, 10 to the 9. This will not affect your results significantly. And I will say, if I'm gonna do a continuous distribution of charges, then the summation is gonna be becoming an integral, and we will talk about these cases in a little bit. Okay, then this is really the problem solving strategy that we are going to use. Here I am talking about just one of the examples from your textbook. It's not an example, it's one of the problems that I'm using as a checkpoint on you, like if you did understand. And here I have two charges, the red and the negative are really, the red and the blue are really placed on the x-axis. This is one-dimensional problem of 2.5 microcoulomb at the origin, and the other, which is negative 3.5 microcoulomb. Remember, micro is 10 to the minus 6, and that one is located at x equals 0.6 meters. Find the position on the x-axis where the net force on a small charge plus q would be 0. Now, here you need to combine, I will say, math with physics, because math itself is not going to work when you are going to solve this problem. Now, one thing that I want you to know, whenever I have two charges that they are really different, that charge is going to occur outside, not between the two charges. If they are like charges, like both positives or both negatives, you are going to find that this point where the force is going to be 0 is going to be between the two charges. Now, of course, I know that if I will put my charge, okay, I don't need to know where, what is really the, the magnitude of this charge. Then I will assume it's at a distance x from that positive charge, and therefore is going to be at a distance r plus x plus 0.6 from the second charge. And I know that it will be attracted to the negative, and it will be repelled by the positive. Therefore, I said F positive equals F negative, and then I said here Q plus divided by x squared should equal Q times Q negative times K, and then the distance, it is x plus 0.6 meters all squared. And then I did now converted my physics into an equation that is going to be a quadratic equation. When I will solve, I was solving for that, I got two numbers. One of them is negative, one of them positive. I will reject the negative. The reason is it's telling me that it might be on the other side, closer to the negative 3.5 microcoulomb, and this is not accepted. It should be closer to the smaller charge, and therefore I will say is gonna be on the, you know, is gonna be at the negative 3.27. It should be on the left, it cannot be on the right, and therefore I did use that 3.27. Okay, which is, of course, as I said, it is to the left of the 2.5. Okay, now I think I'm gonna stop here again, and because this I will move to a new topic.